Okay, conditional probability and independence. That's section 8.3. So what do we do in this section, in this video? Here, we will, no, like I said, I don't need to write that. We'll just say that we will do one is an introduction. And then two, we'll talk a little bit about problems with tables. And that is like in section 8.3, the problems 1 through 20, 33, 34, and 59. And then 3, there are a bunch of problems involving with tree diagrams. And that's problems 25 and 26, 29 through 32, 37 through 40, 49 through 51, and 60 and 62. So really two types of problems here. The problems involving tables and the problem involving tree diagrams. And so part 1 is the introduction. What is conditional probability? And we'll start with that. And then we'll get to what is independence. So we'll start with an example that's sort of a Venn diagram. Suppose we have a coffee shop. And so 50 people at a coffee shop are surveyed. At a coffee shop are surveyed. Great. So what did they find out? They found out that 42 had coffee, 27 had a donut, and that 25 had both. Donut. 25 had both. Right? And so constructing the Venn diagram is pretty easy here. Right? There's our square, our rectangle. There's our coffee drinkers in that circle. There's our donut eaters in that circle. 25 from both, so there's 25 there. That means there's 2 that had donuts but not coffee, 17 that had coffee but not donuts, and then 6 people who were at the coffee shop but had neither donuts nor coffee, and were probably just standing in line or something. Okay, so 50 people total. If you pick one person at random, one person of the 50 at random, what's the probability that they had coffee? Well, there's 42 people with coffee, 52 people total, so 42 people out of 50, that's actually 0.84. So 84% of the people there had coffee. So suppose we do a slightly different thing. If you pick a person eating a donut with a donut at random, what's the probability that they also have coffee? And this is a different question than the previous ones, because here we're adding a little bit extra information. We're only looking at people who have donuts, not all the people in the coffee house. So if we just look at, this is the donut circle, right? So just this circle, what do we find? 25 people with coffee, 2 people without. So probability of having a donut and it's a slightly odd way to write it, but that's how it usually is. The probability of coffee given that they had a donut, right? We only looked at donut people, and we want to know which percentage of them have coffee. Well, 25 of the 27 people, right? There's 27 people with donuts, 25 of them have coffee, and that is actually 93%. So, this little bit of information that we only looked at donut people, that changed the probabilities that they had coffee, right? People who have a donut are 93% likely to have coffee. If we just pick one person at random, then we say, well, there's only 84% chance that they'd actually have coffee. So, coffee drinkers relative to donut drinkers, there's more of them than there are coffee drinkers relative to the entire collection of people in the place. So, this is called a conditional probability. And one can write probability a little tidier than that. Probability. Right? So a little notation. P, A, and then a vertical bar B, like that. This is probability of A given B. I usually think of this as the probability that A happens if B has already happened. Right? So, probability coffee given donut, right? PCD, right? This is the probability that someone who already has a donut also has coffee. And how did we calculate that? Well, we actually took the number of people who had donuts and coffee, that's 25, and divided by the number of people who actually had donuts. So, here, PCD's probability of having coffee given that they have a donut. Okay. Note that probability of C intersection D is probability of having coffee and, right, and donut. D-O-U-G-H-N-U-T. And in this case, that's 25 out of 50. That's 1/2, 4.50. So this is, these two concepts are well, actually very different, right? This is saying we're only interested in donut eaters and which percentage of the donut eaters enjoy a coffee with their donut. This is looking at all the people that go into the shop, including the people who don't eat donuts or coffee, and saying, well, what percentage of the people who go into the shop get both coffee and a donut? So this is sort of different things. This is restricting our world to just donut eaters. This is looking at everybody who goes into the shop. So, what's the formulas for these things? No, where did I write that down? Okay, so some formulas. Probability of A intersection B is defined to be the probability of A intersection B. So this probability of A given B is the probability of A intersection B divided by the probability of B. So that's the conditional probability formula. This is the conditional probability A intersection B over B. Okay, so for us, probability of C intersection D, right? Probability that they have coffee, given that we know they have a donut, is the probability of C intersection D over probability of D. So the probability to have coffee and donut, right, which is 25 out of 50, over the probability that they have a donut. And what's the probability that they have a donut? Oops, where's my Venn diagram? There it is. Probability of having a donut is 27 out of 50, or 54%. And note an interesting thing that happens here, right? The 50s, which is the total number of people in the shop, those cancel out. And so we're just left with the 25 over 27, which is what we had when we calculated the probability of having coffee given that they have a donut. So that's the formula for conditional probability. So the probability of A given B is probability of A intersection B divided by the probability of B. You know, that's the probability of coffee given donut. What's the probability of that of DC equal to? Well, what is this? This is the probability that someone has a donut, given that they have coffee. And another way to think about that is to say, well, look only at the people who have coffee. Only the coffee drinkers. What percentage of coffee drinkers eat donuts as well? Right? This is saying what percentage of donut eaters drink coffee, and that was, what, 93%? 93% of donut eaters also drink coffee. What percentage of coffee drinkers eat donuts? And so again, that's P of C intersection D over now P of C, because we're interested in coffee drinkers. And what percentage of them eat donuts? And so, again, this is 25 out of 50, and now coffee drinkers was, where's my paper with the coffee drinkers on it? 42 out of 50. So it becomes 25 out of 42, which is 25 out of 42. Oh, fudge. I screwed up my numbers. 25 people have coffee and donuts out of 42, and so no. Equals 25 divided by 42.5952. So that's actually 59%. So sorry about having to leave there for a minute. I had calculated the wrong number, so I had to go over to my desktop computer and get out Excel and calculate that. So probability that someone has a donut given that they have coffee is 59%. So 59% of coffee drinkers have donuts, but 93% of donut drinkers have coffee. Great. And so those are conditional probabilities. Given that you know something about a particular group, can you tell something else about them? Note, probability that someone has a donut, right, is 54%. Probability that someone has coffee is 84%. Right? And that's if we go back to the original Venn diagram. That's here, right? 42 out of 50 had coffee, that's 84%. 27 out of 50 had donuts, that's 54%. So, oops, we want all these numbers up here. Probability of a donut eater having coffee is 93%. Probability that someone has coffee is actually 84%. So, coffee, given that they have a donut, is 0.93. Probability of coffee overall is 0.84. What does that mean? If we know someone has a donut, we are more sure they also have coffee. Because if we just look at the 50 people going into the coffee store, what do we know about going into this coffee shop? What do we know? 84% of them come out with a coffee. But if we know they come out with a donut, we're actually really sure, much more sure, well, 9% more sure, that they also come out with coffee, right? Someone who comes out of the store with a donut, we're 93% sure that they actually have coffee as well. So the probability of knowing whether or not they have coffee goes up if we knew that they had a donut. Likewise, P of D given C, right, probability of donut given that they have coffee, that is 59%. And probability of donut is 54%. And so what do we know? Again, if we see someone go into the store, what's the probability they come out with a donut? 54%. But if we see someone coming out of the store with coffee, what's the probability that they also have a donut? So given that we know they have coffee, what's the probability of having a donut? That's 59%. And so again, if we know someone has coffee, we are more sure that they also have a donut. So let's put little quotes around this. Having coffee and having donuts are not independent. Right? And what does independent mean? Well, independent means the probability of something happening doesn't change the probability of the other thing happening. So if we know someone has coffee, are they more likely or less likely to have donuts than otherwise? Well, yeah, they're more likely to have donuts. And if someone has a donut, are they more likely or less likely to have coffee as well? They're actually more likely to. But what we don't see here is that, you know, if you have donuts, then having coffee doesn't change the percentages at all. So, independence if P of A given B equals P of A, then A and B are independent. And note that I'm not boxing this yet, right? Because this is sort of one concept of independence. And so this is saying you have certain probability of something happening. Suppose you know, you get some extra information that something else has happened first, B. Does that change the probability that the event A happens? And if it doesn't, if knowing B doesn't change the probability that A happens, then they're called independent. So here, we know what the probability of having a donut is. It's 54%. If we know that they have coffee, does that change the probability that they have a donut? And the answer is yes. So they're not independent. People who have coffee tend to have donuts more often than people who don't, than the general population has donuts. Right? Coffee drinkers tend to eat more donuts than people in general. So they're independent. And note this is also, right, if PBA equals P of B, right? Because it doesn't really matter, right? We're talking about whether or not A and B are independent, right? So what we found here is that knowing people had donuts increased the probability that they would also have coffee. So, test for independence. How do you tell if two things are independent? Well, one way is to calculate these things, but if we take this formula and take it apart a little bit, what do we have? We have P of A given B. The definition of that, if we go up to the first box thing, is P of A intersection B over P of B. This thing should go away if I can. P of A intersection B over P of B. Great. And we want to know is that equal to P of A? Well, let's do this. So, P of A intersection B over P of B equals P of A when A and B are independent. Or finally, P of A intersection B equals P of A times P of B when A and B are independent. Great. So, what's the test for independence then? We'll put a little question mark at that one, so because now we have the test for independence. One, find, well, let's not say find, let's say calculate P of A times P of B. 2, calculate the probability of A intersection B. 3, if your answers to 1 and 2 are same, then they're independent. A and B are independent events. If your answers to 1 and 2 are not same, then they're not independent. And so we'll put a box around that, because that's the test for independence. And the idea of independence is that, you have two events. If one of them happens, does that change the probability of the other one happening? If it does change the probability of the other one happening, then they're not independent. The first event affects the second event. And this is a way to check on whether or not something is independent. So, having a donut and having a coffee are not independent thing. If you see someone with a donut, you are more likely to think that they have a coffee than the general population. If you see someone with coffee, they're more likely to have a donut as well. Okay, so we can set this up as a little bit of a table. We'll actually set it up as a probability table. It's a Venn diagram. We can turn Venn diagrams into tables. One, two, three, four. This is donut, total, coffee, not coffee, total. What's the probability that someone had donut and coffee? Well, that was 50%, right? 25 out of 50. What's the problem that someone had coffee but not a donut? If you go way back up to the Venn diagram, coffee but not a donut is 17 out of the whole 50. So that's 34%. So what's the probability someone has coffee but not a donut? That's 17%. 34%. Right? Coffee, donut but no coffee, that was 2 out of the 50 people, so that's 0.04. And neither coffee nor donut, that was the 6 people. That's 0.12. So we can take our Venn diagram tables and just divide everything by the total number of people, and that gives you a probability table. And you can add up the probabilities. 84% of the people had coffee, 16% of the people did not have coffee, 54% of the people had donuts, 46% of the people did not, and of course the totals have to add up to a probability of 1. So reading this table, what's the probability that someone has a donut? Well, probability of donut is 0.54. What's the probability of coffee and a donut? Well, that's 0.50. What's the probability of coffee and then, of having coffee given that they have a donut? Well, you take probability of C intersection D and you divide it by the probability of D. So it's this number, 0.50, divided by that number, 0.54. And that's the 93% that we found before. Right? And likewise, P of donut given coffee, right? What's the probability that you have donut and coffee? That's the 50%. What's the probability that you have coffee? That's this 84%. And that should be my 0.53. So 0.5, what was it? 0.59 that we had before. Okay, so if you have a little table of possible outcomes for a Venn diagram, you can calculate probability of something, the probability of C intersection D, probability of C and D, probability of D and C. Are D, C independent? How would you test that? Well, 1, calculate P of C times P of D. So the probability of having coffee is 84%. The probability of having a donut is 54. And 0.84 times 0.54 is, let's see, 0.45. Right. What's the probability of having a coffee and donut? 0.50. Answers to 1, 2 are not the same, so not independent. And so that's how the test for independence goes. Okay, so we can look at other sort of examples for these things. We can look at a slightly larger table, and this is covering problems. Where's my list of problems now? Table problems, so 1 through 20, 33, 34, and 59. So we'll expand our coffee shop example a little bit. We'll put up a table, and again, this is a table of probabilities. So people come in, they can have donuts, they can have pie, or they could have a muffin. Right? And they get either coffee or tea. And we're going to pretend that everybody either gets coffee or tea and either gets donuts, pie, or muffin. Okay. So, and suppose the table is set up like this. So what are these numbers? These are the numbers of people who do both things. So 40% of all people who come into this particular coffee shop get a muffin and a coffee. 10% get a donut and tea. Nobody gets tea and pie, although 15% people get coffee and pie. So what percentage of people come in get donuts? Well, 35%. How many get pie? 15%. How many get muffins? 50%. And of course this adds up to 100%. How many people get coffee? 40 plus 40 is 80% of people get coffee, 20% of them get tea. So that's 100% as well. Great. So we can ask questions about these things. For this particular coffee shop, what's the probability of C given D? Or what's the probability that if someone has bought a donut, if you see somebody with a donut, what's the probability that they also have coffee? Well, again, that will be probability of C intersection D over probability of D. It's always the given part that's in the denominator, so 0.25 over 0.35. And that's 0.72. So 72% of donut eaters have coffee. Okay. What's the probability of having coffee? Right, that's 80%. This suggests that if you see someone with a donut, it's less likely they have coffee than if you just see someone at random, right? 80% of the people in the store have coffee, but only 72% of the donut eaters have coffee. Okay. That suggests that these are not independent. Well, let's check. What's our thing? Well, we calculate probability of coffee times probability of donut. Probability of coffee is 80% times probability of donuts, that's 0.35%. And 80 times 0.35, I really should have done all this before, equals 0.8 times 0.35 is 0.28. So 0.28. 2, what's probability of having a coffee and a donut? Well, that's 0.25. So 3, since these answers are different, the two events are not independent. What you know is that if you see someone with a donut, they're less likely to be drinking coffee than the people in general. Okay, for this particular coffee shop. What about muffins? Right? Some people have muffins, some people don't have muffins. So, probability of having coffee and a muffin is 40%. So 40% of the people get coffee and muffin. What's the probability of having muffin given that you know someone has coffee? So we're looking at coffee drinkers only, and we're asking, well, what's the probability that people who drink coffee eat muffins? So what is that? Well, that's going to be probability of muffin intersection coffee over probability of coffee alone. So muffin intersection coffee we know is 40%. What's the probability of having coffee? Probability of having coffee is 80%. So 0.80. So that's 1/2, 50%. What's the probability that someone in the store has a muffin? Well, probability that someone in the store has a muffin is also 50%. Right? So if we look at people who are just coffee drinkers, what percentage of them have muffins? Well, 50%. What about people overall? We just look at the store. What percentage of them have muffins? Well, 50%. So what we're seeing is that knowing that people drink coffee doesn't tell us anything more about whether or not they eat muffins, right? Half of the population are muffin eaters, and half of the people who drink coffee also eat muffins. So they are independent events, and we can calculate them. RCM independent, right? Probability of C times probability of M. What's the probability that someone has coffee? That's 80%. 50% have muffins. So it's 0.8 times 0.5. That equals 0.4. Probability of seeing someone who has coffee and a muffin, well, that's also 0.4. Answers are the same. So independent. And so that gives us our test for independence. Right? So in this particular case, right, 80% of muffin eaters drink coffee, 80% of the entire population drinks coffee, so knowing that people eat muffins doesn't tell us anything about whether or not they drink coffee. We do know that people who are donut eaters are less likely to drink coffee than people overall, because those are not independent events. Okay, so if you have a table of probabilities, you can calculate what the various probabilities are, what the various conditional probabilities are, and whether or not events are independent. So 1 through 16 are all 1 through 20 are all just sort of, there's a big table and you just have to do the calculations. It's really aimed at getting you to be used to the formulas. Tree diagram problems. Tree diagrams. So these are really useful things. And we'll ask a question. Roll a die twice. What's the probability to get 2 or 4 on both rolls? And that is actually just a multiplication principle, right? We want to know what's the probability of getting a 2 or 4 on the first roll, what's the probability of getting a 2 or 4 on the second roll, and you multiply them together. Let's see. Yeah, so that's 1/3, and that's 1/3, right? Because there's 6 possible outcomes: 1, 2, 3, 4, 5, 6, 2 or 4, 2 or 4, so 1 out of 9. So about 11%. And we can do this as a tree diagram. We'll let A be roll a 2 or 4, and B be roll a 1, 3, 5, or 6. Right? And so how do we draw a probability tree diagram? Where there's my 2 events. We start here, and either A happens or B happens. And there's a 1/3 probability of A and a 2/3 probability of B. And then once A or B has happened, you roll it again. What are the 2 possible outcomes? You could have A or you could have B. What's the probability that you roll a 2 or 4 in the second roll? Well, 1/3 and 2/3. A and B, 1/3 and 2/3. Great. So this branch, right, A and then A, this is a probability of rolling a 2 or 4 on the first roll and a 2 or 4 on the second roll, and the probabilities, you just multiply them together, 1/9. So this is a probability of having A happen on the first roll and B happen on the second roll. That's this branch, first A and then B. And so that's going to be 1/3 times 2/3, which is 2/9. And then this of course is the probability of B and then A. What's the probability that you roll 1, 3, 5, 6, and then you roll 2 or 4? That's 2/3 times 1/3. You just multiply the probabilities. That's still 2/9. And then we have 4 cases left to consider, and those are probability of rolling a 1, 3, 5, 6. That's 2 over 3 times 2 over 3, which is 4/9. Great. And so there's our probability tree, right? And it tells us a lot of probabilities. And we can ask a question like, what's the probability of getting 2 or 4 on the second throw? And this is what we called event A. So what's the probability that you get A on the second throw? Well, there's 2 ways to get A on the second throw. Either this branch, so that's probability of A comma A, or, and whenever we're doing or, that's an addition, right? Probability of B and then A. Right? So that'll be 1/9 for this branch plus 2/9 for this branch, which is 3/9, or 1/3. Which isn't actually surprising, right? When you roll a die, it doesn't matter whether it's the first throw or the second throw or whatever, right? You've got a 1/3 chance of getting a 2 or a 4. But once you have a tree diagram, you can actually count things like what's the probability that you get A on the second event, and that's these 2 branches added together. Okay, so there's a tree diagram. Here's a slightly different tree diagram. Draw 2 cards from a deck. From a standard deck, without replacement. What does that mean? Well, it means that I take the card out and I put it down on the table, and then I pick another card out and I put it down next to it. I don't take the first card and put it back in. That would be with replacement. So with replacement, you take a card out, you look at it, you write down what the result is, you put the card back in, and you pick again. Without replacement means take a card out, put it down on the table, take another card out, put that down next to it, and then look at it. So let S be the probability that you draw a spade. No, be the event that you draw a spade, and D be the probability that it be the event that you draw a diamond. Okay, so we can set up our probability tree. SD. What's the probability of getting a spade? 13 out of 52. What's the probability of getting a diamond? 13 out of 52. Because there's 13 spades, 13 diamonds, and 52 cards. What's the probability of getting a spade on the second draw? Well, we have to be a little bit careful here because our deck has changed. We've taken one of the cards out. In fact, we took a spade out, and now we're going to draw another card. So how many spades are left in the deck? Just 12. How many cards are left in the deck? 51. So 12 over 51. But when we're looking at the probability of drawing a diamond, given that we've already drawn a spade, well, there's 13 diamonds and 51 cards left, so it's 13 over 51. Likewise, when we're talking about the probability of drawing a spade, given that we've already drawn a diamond, well, there's 13 spades left, but only 51 cards. And likewise, the probability of drawing a diamond, given that we've already drawn a diamond, is 12 over 51. So let's note, probability of drawing a diamond on the first draw, that's the 13 over 52. Probability of drawing a diamond given that you've already drawn a diamond, right? So given that we've already drawn a diamond, what's the probability that we get the second diamond? That's 12 over 51. Right? And so that's a conditional probability. Given that we've drawn a diamond, what's the probability that we get another diamond? So these are all conditional probabilities. Okay. And what are these probabilities? What's the probability of getting a spade and then a spade? Well, that's 13 over 52 times 12 over 51, and if you multiply that out, it becomes 0.058. 0.89. Probability of getting a spade and then a diamond is 13 over 52. Right? This number times that number, 13 over 51, which is 0.0637. And probability of getting a diamond then a spade, that's this branch, and that's actually also 0.0637. And probability of getting a diamond and then a diamond is 0.0589. And these don't add to 1 because, you know, there are other cards in the deck, right? There's an entire 50% chance that your first draw would be either a club or a heart, and so, you know, these probabilities aren't going to add to 1. Great. So, what's the probability that we get both spades? Well, there's only one branch that gives us 2 spades, so that's the probability of this, so 0.0589. What's the probability that we get a diamond given that we have a spade? Well, as we pointed out, spade first and then diamond, that's 13 over 51. Right, so that conditional probability is 13 over 51, whatever that happens to turn out to be. And what's the probability that we have the second card is a diamond? Well, there's 2 ways to get that. You can get a spade and then a diamond, plus a diamond and then a diamond. So those are the 2 ways to get a diamond as a second card. This is 0.2549, by the way. Excuse me. And so that's going to be 0.0637 plus 0.0589, which is 0.1226. So about a 12% chance that you'll draw either a spade or a diamond, and then a diamond. Right? So once you have this, you can sort of figure out which branches are the ones that you want to run down. Okay, so another tree diagram. We have a box with 7 red, 4 white, 10 green marbles in it. Right, so little pieces of colored glass, 7 of them are red, 4 are white, and 10 are green. What's the probability? And you draw 2 without replacement from the box. So you take one out, you put it aside, and you take out the other one. So what's the probability that you get 1 red and 1 white? Well, 2 cases. You can either draw a red one and then a white one, or you can draw a white one and then a red one. Right? Those are the 2 ways you can end up with 1 red marble and 1 white marble. What's the probability of getting a red one and then a white one? Well, the probability of drawing a red one first is 7 out of the 21 total, times then drawing a white one. So what's the probability of drawing a white one if you've already drawn a red one? Well, we're down to 20 marbles, but they still have the 4 whites. What about white and then red? Well, 4 whites out of 21 total, times, well, drawing a red after a white means that you're down to 20 marbles because you already picked one out, but you still have all 7 reds. So 7 over 20. And if you multiply that out, it's about 0.133 ... Right? So multiplication principle, right? There's a tree diagram lurking behind this, and we'll get to that in a second, but sometimes it's nice to be able to do these without having drawn out the tree diagram. What would be the probability that the second marble is green? And that's supposed to be an is, and this is supposed to be a marble. Well, how many ways are that you can have a second marble as a green? Well, that means you could start with a red and then a green, or you could do a white and then a green, or you could do a green and then a green. And what are the probabilities of that? Well, probability of drawing a red is our 7 out of 21. Probability of then drawing a green, well, again, we're down to 20 marbles, and we still have all 10 green ones. White and then green, well, 4 white out of 21 on the first draw, and then 10 out of 20 for the second draw. Green and then green, that means 10 out of 21 on the first draw, and then 9 out of 20 on the second draw, because if we've already taken one green out, we have 9 greens left out of the 20 that are left. And so that gives me a 0.4762. Right? And so you can think about these kinds of problems in terms of tree diagrams by saying, well, what's the tree diagram here? It's a little bit of a big one. You can do red, green, or white on the first pick, and then you can do red, green, or white on the second pick for each one of those choices. And the probabilities for each choice varies, right? On the first pick, there's 21 in the box, 7 red, 10 green, and 4 white. On the second pick, there's only 20 in the box. So all these conditional probabilities, this is why these big tables are a pain, are all out of 20. Right? Because there's only 20 marbles if you're picking without replacement. So if you've already picked one red, you've only got 6 reds left, but you still have all 10 greens and all 4 whites. If you already picked one green, you only have 9 greens, but you still have all 7 reds and all 4 whites. And if you've already picked one white, then you have 3 whites, you have all 10 greens and all 7 reds. And so those are the various probabilities. For this one red and 1 white, we're looking at this branch, and here's white and then red, this branch. Right? So 7 over 21 times 10 over 20, that's this one, and then 4 over 21 times 7 over 20, that's that one. It's probability that the second marble is green. We want this or that. Right? Those are the cases where you have the second marble is green. That'd be red, green, 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 white, green, and those are those 3 cases. So the more options you have, the bigger the tree diagram. And so it's useful sometimes to be able to think about what the outcomes of the tree diagram would be without actually drawing the whole tree diagram. And lastly, like the word problems, suppose a licensure exam can be taken 3 times. And what they find is that 60% pass the first time. Of those who didn't pass, the first time, 45% pass the second time. And of those who have to take it a third time, and 20% taking a third time passed. Okay, so what is this 45%? Well, the way this is phrased, this is a conditional probability, right? It's given that we know someone hasn't passed it the first time, what's the probability that they pass it? It's 45%. So what's the tree diagram here look like? Well, there's 2 options. It's a little bit different from the previous tree diagram because it's not actually symmetrical. There's 2 options. There's pass and fail. 60% pass the first time, 40% fail the second time. For the people who pass, they never take it again. The people who fail, we get a branch from them, right? Either you pass or you fail. 45% of those who have to take it the second time pass. That means 55% fail. And then we get a third branch. These people are okay, but you know, if you failed it twice, you got to take it again, right? And you can pass or you can fail. 20% of these people, that means 80% of those. So this number here, this is the probability that you pass given that you failed the first time. Right? And then this is the probability that you pass given that you failed the second time. So these are all conditional probabilities. You know, and we can ask questions. What's the probability fail all 3 times? Well, 0.4 times 0.55 times 0.8. This branch is failing all 3 times. And if you multiply that out, you get 0.176. What's the probability that someone passes on the second try? Well, that's this branch. 0.4 times 0.45, which is 0.18. So 18% of the people actually fail the first time and pass the second time. 17.6% of the people fail all the way through. 60% of the people pass right away. And you can think of this as sort of a weird Venn diagram. Suppose 1,000 people took this test. What do we know? So here's our 1,000 people. We know that 60% passed on the first try. So that's 600. And then we know 40% failed on first try. And that's 400. Okay. But this gets subdivided, right? 45% of them passed. And that's 180 on the second try. Right? And this whole thing here is our 400 people who failed in the first try. So 180 of those passed on the second try. 400 minus 180 is 220. These are the people who had to take it a third time. And what do we know about the people who took it a third time? 20% of those passed. And so 44 passed on third try. So 44 of the 220 passed on the third try. That means 176 failed. So if we look at our batch of 1,000 people, 600 passed on the first try, 180 passed on the second try, 44 passed on the third try, 176 failed altogether. So there's our 176. Right? Those the percentage of the people who failed all the times is 176 over 1,000. What about people who passed on the second try? Well, 180 of that, 180 over 1,000, that's our 18%. So sometimes it's useful to think about some of these problems in terms of, suppose you had 1,000 people, what would they do? At the end of the road, what do we have here? Conditional probability is given by, boop, 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 all the way back up here, this formula. This is A given that B happened, and it's probability of A intersection B divided by probability of B. Independence, right? If the probability of A given B is the same as the probability of A, if knowing that B happens doesn't change the probability